Building a true traversable wormhole might be feasible, but only in the event that there are other dimensions to our universe. A wormhole is created when parts of the universe are fused together and joined by a tunnel or bridge, commonly referred to as a throat. You can choose how big or long this throat is, but generally speaking, you want it to be less than the average distance to your destination. According to Einstein's general theory of relativity, creating a wormhole is really simple, but regretfully, wormholes' greatest drawback is their extraordinary instability. The biggest problem with wormholes is that they are unstable. As soon as they form, their enormous gravitational strengths, because they are literally made of black holes, rip them apart faster than the speed of light, which makes them rather useless as actual shortcuts through the universe. The only known way to stabilize a wormhole is to use some form of exotic matter. Exotic matter can take the form of matter with negative mass, which doesn't appear to exist in the universe, or some other scenario that violates what are known as the energy conditions of general relativity. The energy conditions simply state that everybody should experience positive energy, on average, pretty much everywhere they go in the universe. To stabilize a wormhole, a traveler would have to experience a region of negative energy. This negative energy would balance out the positive energy of the mass of the traveler, keeping the wormhole open as they pass through it. Certain physical situations can occasionally result in the violations of certain energy criteria. That being said, physicists are unaware of a single occurrence in which the entire set of energy criteria is, on average, broken over extended periods of time, precisely what is required to create a wormhole. There is no force in nature that is as weak as gravity, but the reason gravity is so weak is beyond our understanding of physics. Some theories suggest that reality has more spatial dimensions than the standard three, drawing inspiration from string theory's idea of numerous extra spatial dimensions squeezed to microscopic sizes. These theories treat our three dimensions as merely a brain, a thin membrane existing inside a higher dimensional bulk. It's not a given that those extra dimensions are enormous. If they were, we would have observed particles coming and going from the extra dimension. In this case, gravity is the only force that may move through the bulk, and all other natural forces and particles are restricted to the three-dimensional brain. Therefore, gravity may be as powerful as all other forces combined, but our three-dimensional perception of it makes it seem feeble since it is so greatly diluted throughout all the other dimensions. These brain-based theories provide fresh avenues for investigating the nature of wormholes since they are attempts to comprehend gravity. General relativity governs our understanding of wormholes. However, it's likely that the existence of extra dimensions modifies general relativity and opens the door to the possibility of wormholes. The researchers also speculated that the existence of other spatial dimensions beyond the standard three could be indicated if humans were to witness or create a wormhole in the future. What we need is a quantum theory of gravity, which is the theory of strong gravity at small scales, but we don't have one. The Einstein-Podolsky-Rosen, or EPR in short, is about pairs of particles that seems to be connected by a wormhole, or Einstein-Rosen bridge, according to the physics conjecture ER equals EPR. This conjecture is believed by some to be the foundation for combining general relativity and quantum mechanics into a theory of everything. In 2013, Leonard Susskind and Juan Maldacena put forth the hypothesis. They postulated that a pair of maximally entangled black holes is comparable to a wormhole, sometimes known as the Einstein-Rosen bridge or ER bridge. The term quantum entanglement is known as EPR. This is created from the initials of the surnames of the authors of the first papers on entanglement written by Albert Einstein, Boris Podolsky, and Nathan Rosen, and a paper on wormholes written by Einstein and Rosen. The authors of the two papers, both published in 1935, did not assert any relationship between the ideas at that time. Fast forward several decades, Leonard Susskind and Juan Maldacena proposed gathering up all the Hawking particles that escapes of black holes and compress them together until they collapse into a new black hole. The newly formed black hole would be entangled connected via wormhole with the original black hole. That trick transformed the confusing mess of Hawking particles, making them paradoxically entangled with both a black hole and each other into two black holes connected by a wormhole. In this way, the entanglement overload is averted and the firewall problem goes away. This is a conjectured resolution to the AMP's firewall paradox. Whether or not there is a firewall waiting for us at the event horizon depends upon what is thrown into the other distant black hole. However, as the firewall lies inside the event horizon, no external superluminal signaling would be possible. This hypothesis is an extension of the finding that two maximally entangled thermal conformal field theories are dual to a maximum extended ADS-Schwarzschild black hole, a non-traversable wormhole, through the ADS-CFT correspondence. They supported their conjecture by demonstrating that, in addition to producing entangled black holes upon Wick rotation, pair creation of charged black holes in a background magnetic field also produces wormholes. This conjecture appears to be at odds with quantum mechanics linearity. A linear superposition of separable states is called an entangled state. Although separable states are presumably not connected by wormholes, a wormhole connects a superposition of such states. The scientists expanded on this conjecture by asserting that Planck-scale wormholes can connect any entangled pair of particles, including ones that aren't often thought of as black holes, differing masses or spins or charges that aren't opposing. This conjecture leads to a more ambitious one. Entanglement determines the geometry of space, time, and gravity. Wormholes are remarkably simple to construct, at least in theory. The link between matter and energy, as well as space and time, is defined by gravity in Einstein's theory of general relativity. The key to constructing a wormhole lies in identifying a specific arrangement of matter and energy that enables the creation of a passage, commonly referred to as a throat in the field of wormhole investigation, connecting two remote locations in space. In principle, the length of the throat can vary, but the most intriguing wormholes occur when the throat is significantly shorter than the typical distance between 2 points. This characteristic renders the wormhole a convenient shortcut. Additionally, wormholes can function as time machines, transporting individuals to either the future or the past, contingent upon their construction. To address these issues in general relativity and establish stability in a wormhole, a cosmic traveler must construct the wormhole using an exceedingly rare component, namely a type of matter possessing negative energy or mass. The concept of negative mass is derived from the notion that an object with a weight of negative 10 kilograms would possess negative mass. Negative mass has not been observed by scientists in any region of the cosmos. Negative energy is a state in which the energy in a specific region is negative compared to its surroundings. However, this can only be produced at the quantum scale. The existence of this issue is crucial as it serves to prevent the collapse of the wormhole throat upon a traveler. However, it also presents certain challenges. The material exhibits a negative mean energy density, a highly uncommon attribute of matter in the cosmos that is only detected in highly particular circumstances at the quantum scale. Given the scarcity of such stuff, the construction of a whole wormhole using this exotic material would appear unattainable within the confines of our universe. Despite the presence of null geodesics that travel through the wormhole, it is observed that these geodesics are confined within a black hole, hence impeding their ability to traverse vast distances. Based on our analysis, it can be inferred that Einstein-Dirac-Maxwell wormholes lack traversability. The concept of exploring other solar systems beyond our own, or even other galaxies, with the potential to encounter extraterrestrial civilizations, as well as the notion of revisiting past events without the need to await the future, has long been a subject of human imagination and fantasy. Wormholes offer a relatively straightforward and cohesive resolution to these predicaments. However, wormholes that are formed according to the conditions established by general relativity encounter a significant drawback. They lack the ability to be traversed. Event horizons, which are unidirectional barriers in space, conceal the entrances of general relativity wormholes. Consequently, if one were to venture into the wormhole, it would be impossible to exit, so undermining the intended objective. Another issue that arises is their significant instability. Upon the entry of a solitary photon, or light particle, into the throat, the entire wormhole undergoes a catastrophic collapse prior to the egress of that light packet.
ER stands for Einstein and Rosen. Stands for Einstein and Rosen, who wrote a famous paper about gravity in 1935. EPR stands for Einstein, Podolsky, and Rosen. Podolsky was another one of Einstein's collaborators who wrote a famous paper about quantum mechanics that same year, 1935, having little idea, I suspect, I don't believe they had any idea, that the two were intimately related. Einstein-Rosen and Einstein-Podolsky-Rosen. Now, what are they? We're going to spend a little bit of time explaining what they are and how odd and bizarre they are. Let's start with the idea of a formation of a black hole. Very simple. A cloud of particles indicated by a bunch of little points collapses under its own weight due to its own gravitation. The particles get pulled together by gravity, and what happens to them? Eventually, they form a black hole. That's the basic process that we'll be interested in. And of course, there's no reason why there should only be one black hole in the world. Two clouds of gas, somewhere in distant parts of the universe, could independently collapse and form two black holes. We could call one of them Alice's black hole. I suppose that's the one on the left. Bob's black hole, he's a little fellow. Can you see Bob? I can't, yeah, there's Bob. Bob, that's Bob's black hole. There's Alice's black hole over there. And just two black holes. What do they have to do with each other? Not much. They were formed independently. They're uncorrelated. They're not interacting with each other because they're too far away from each other. And so we would say that they're statistically and dynamically and in all ways independent of each other. No interactions, no correlations. And if perchance Alice happened to fall into her black hole, that would be the end of her. If Bob fell into his black hole, that would be the end of him. End of story. Okay? Now, what I want to imagine now is that we formed the black, well, no, let me come to, I am tired. Let me come to another issue now. That was black holes. We'll have more to say about black holes, clearly. But before we do, I want to talk about entanglement. Entanglement is the thing that Einstein, Podolsky, and Rosen discovered. Okay? What is entanglement? Entanglement between systems. It could be entanglement between two electrons. It could be entanglement between two photons. It could be entanglement between, well, any two things. Entanglement is a quantum mechanical, it's the quintessential quantum mechanical property that systems can have, pairs of systems, that never makes any sense classically. If I were to tell you that I know everything that there is to know about a pair of systems, these two things over here, if I know everything that can be known about the composite system made out of these two things, what are these things anyway? If I were to tell you that I know everything, or that everything that can be known about a system is known, you would say, well, that must mean that everything about the parts of the system are known. How can it possibly be that you know everything that can be known about a system and not also know everything about the two parts of the system? Well, in quantum mechanics, that can happen. You can know everything about a pair of electrons. This is supposed to be a pair of electron spins. The spin can be up or it can be down. Two electrons. And for those who know a little bit about entanglement, you'll recognize this as an entangled state in which you know nothing about the first particle. What do I mean by you know nothing about it? It could equally well be likely to be up or down. So if it's equally likely to be up or down, you know nothing. The second particle can equally well be down or up. Again, you know nothing, and yet this is as complete a description of this state of an electron, of a pair of electrons, as you can possibly have. What do you know? What you do know is correlation. You know that if the first electron is measured to be up, the second one is definitely down. If the first one is measured to be down, the second one is necessarily up. It's either this or this. That's the character of entanglement. Something that never happens classically. As I said, if you know everything there is to know about a system, you know everything about its parts. Not so quantum mechanically. Two particles which are entangled in this way are usually called Bell pairs. Bell doesn't stand for the thing that you make a sound with. John Bell, the physicist John Bell, who spoke about a great deal of this and added a great deal to it. But this is essentially the Einstein-Podolsky-Rosen idea of entanglement. And we usually use a little graphical notation to indicate that two particles are entangled, namely just draw a line between them, and that indicates that they're entangled in this funny way. Okay, now, let's imagine again that we're going to create two black holes, but instead of just creating them independently, what we're going to imagine is that we create first a bunch of Bell pairs, a large number of particles which are entangled with another large number of particles. This particle is entangled with this one's entangled with this one. We create them in the laboratory, and then we separate them. Separating them does nothing to destroy the entanglement. And so what we wind up with is two entangled clouds of particles, and then on each side, the particles collapse to form black holes. What does that make? Well, it makes two entangled black holes. That means that if you measure something about one black hole, you learn something about the other one. If you measure something about this one, you learn something about this one. Two entangled black holes, Einstein-Podolsky-Rosen entanglement, in this case between black holes. And this is something that, it's not something you're going to do in a laboratory. We're not going to make blacks in a laboratory. But in principle, this is something that could be made. Okay. What's new about it? How are the entangled black holes different than the unentangled black holes? And here is where something strange happens. I'm not going to prove it. I'm going to tell you this is the outcome of many years of research, the last 20 years of research, 20, 25 years of research. We'll talk a little bit about it, but I'm going to tell you right now what has been learned. Now, take a look at this. This is supposed to be space. Why have I bent it over like that? Bending it over like that does nothing real to it. If I have a piece of paper and that piece of paper is flat, if I bend it like that, that does not change the geometry of the sheet of paper. The intrinsic, it's called the intrinsic geometry. The intrinsic geometry is the same whether it's this way or this way or this way or this way. But just so I can make a point, I've taken space and folded it over so that this region over here is close to that region on the diagram. These two places are very far apart. If Alice wants to get to Bob, she has to walk all the ways around here. Alice and Bob have created a pair of entangled black holes. The new thing, because they're entangled, is that an Einstein-Rosen bridge forms between them. An Einstein-Rosen bridge is popularly called a wormhole. It's a route through space which short-circuits the long distance between these. This is, to my mind, one of the craziest things we've discovered in the last 20 years, that the existence of entanglement creates spatial connectivity between two regions which would otherwise be very, very far apart. Now, does that mean, Does that mean that Alice can send a signal to Bob, short-circuiting the long distance between them? No, it doesn't. Entanglement does not provide a way of sending messages. It's correlation, but it's not message sending. Alice cannot, when we're going to come to the reason why soon enough, why Alice can't use this wormhole, this Einstein-Rosen bridge, to send a message directly to Bob. She cannot violate the rule that to send a signal from one place to another place, that it goes faster than the speed of light. It would be going faster than the speed of light, at least the speed of light around this direction, if Alice could send a message to Bob. There are two ways to think about this. From the point of view of entanglement, there's a theorem. The theorem says that entanglement can never be used to send a signal from one place to another. It's correlation, but it's not signal sending. From the point of view of general relativity, from the point of view of these wormholes, it's the non-traversable character of wormholes that you cannot cross from one to the other, from one side to the other. I'll explain why that's true, but not yet. Okay. But nevertheless, despite the fact that Alice and Bob cannot send messages through the wormhole, there is something else that's extremely odd. And this is a property of general relativity. It's a property of these Einstein-Rosen bridges, namely that Alice and Bob can decide to jump into their respective black holes and meet at the center. So let's just review. We take these entangled particles, we separate them out to the ends of the universe, we collapse them into black holes, and then Alice jumps into her black hole, Bob jumps into his black hole, and they can meet in the center after a very short time. That is a remarkable conclusion if it's true. But the only thing, whoops, let's go back. The only thing is that their meeting at the center can never be, how shall I say, can never be reported to the outside. They are stuck behind the horizons of these black holes. They've jumped in, they're behind the horizons of the black holes, and they cannot report to the outside world that they've discovered each other on the inside. So somebody on the outside will not experience any indication that something very strange has happened because of this entanglement. Okay, for the experts. For the experts, here's the proof. The proof is a Penrose diagram. If you've seen Penrose diagrams before, you'll know what this is. If you haven't, it's just what I said on the previous slide. This is a picture, a diagram, a mathematical diagram of the two black holes that were created very, very far apart, but in which you can pass from one to another through a wormhole. What this picture is saying, what the previous picture is saying, is that Bob and Alice can jump into their respective black holes and meet at the center. All right, so that's a mathematical proof. Did you catch the proof? No equations, but a mathematical proof that two entangled black holes, and they are entangled, two entangled black holes can be used not to send a message through. Notice, you cannot send a message from this side over here to this side over here. That would exceed the speed of light, but the two participants can jump in and meet at the center. That's a crazy thing.